This is the Chem 1 lecture over the introduction of the periodic table. So we just finished Unit 4 where we were writing electron configurations. And can you imagine not having a periodic table? That would have been incredibly difficult because the periodic table allowed us to see the fill order in our sublevel blocks and was a very useful tool to us. So it's still going to be useful. Today we're going to figure out who are the people responsible for the order of this periodic table and what other information can we get out of the periodic table. The first guy of two that you need to know is a guy named Dmitri Mendeleev. He is known as the grandfather of the periodic table, and he organized elements based on their reactivity and then ordered them in terms of their atomic mass. Okay? And he even left spaces for elements that were not yet discovered, but he was able to make predictions of what their reactivity would be and around what mass they would have. So once again, Mendeleev ordered the periodic table by the average atomic mass. So Mendeleev's predictions came true when scandium, gallium, and germanium were discovered, and they were super close to what he had predicted on his periodic table. Therefore, people accepted his periodic table. However, there was a hang-up with Mendeleev's table. If we focus on the two elements argon and potassium, if we were following Mendeleev's arrangement, potassium would have been ordered first in his periodic table and then argon, because argon has the higher mass. But what we observed with their properties is argon is very non-reactive and it fit better coming before potassium. Potassium fit, where we see it now, with the alkali metals as a really reactive metal, but it didn't match up with the mass. So it made us reconsider that maybe ordering the periodic table by mass isn't the best number to be ordering the table by. As you might have guessed, today's periodic table that you have is not arranged by atomic mass, but by the atomic number, also known as the number of protons. So if we look at that top number, they are numerical all the way across the energy levels. And so now we're going to talk about the scientist who came to that conclusion. Henry Moseley is now known as the father of the periodic table. So Mendeleev is the grandfather because he was the first, and then Henry Moseley is the father of the modern periodic table, and he was the one to propose that we should arrange a periodic table by the protons, by that atomic number. Sadly, Henry Moseley's contribution to the world was ended when he was sent off to war and was killed on the front lines at the age of 28. So because of this loss, the British government later restricted its scientists to non-combative duties during World War II. Okay, now we're going to look at the periodic table and see there's some different organization to it. So you should hopefully have like 3 highlighters out or 3 different colors. And one way you can look at the periodic table is in blocks of metals, nonmetals, and metalloids. So I want you to take an opportunity. You can either outline, you don't have to maybe shade in every box to save time, but most everything on the left of your periodic table is a metal, with the exception of hydrogen. So be careful not to include hydrogen as a metal. Most of everything to the far right of your periodic table are nonmetals, and then there's going to be what we call kind of like a zigzag staircase, and those are called metalloids. So take a moment to color coordinate what the periodic table is with the breakdown of metals, nonmetals, and metalloids. Okay, we want you to know about properties of these 3 sections. So the first one we're going to talk about is the largest section, which is the metals. So the majority of our periodic table are metals. And so you probably already know these properties, but metals are shiny. They're typically solid at room temperature. They have a high melting point as well as a high density. You can hit metals or hammer metals and they're not going to break. We call that malleability because they're bendable. You can also take a metal and draw it into a wire, and we call that ductility. So I think of like copper wire in our houses. And then why we use copper wire in our houses is because metals are good at conducting heat or electricity. So our copper wires are going to carry electricity around our house. We learned from last unit that metals typically have low valence electrons, and so in their quest to have 8 valence electrons, they prefer to lose their electrons, and when they lose something negative, they become positive, and we call that cations, so a charged particle with a positive charge. Properties of nonmetals, and so once again we're focusing on that right side of the periodic table as well as hydrogen. Don't forget hydrogen. They're pretty much opposite of a metal. So they're not shiny. They're not good conductors of heat or electricity. If you hit them, they're probably going to break. They have a lot of valence electrons, so they are close to that stable 8 valence electrons. So they want to gain electrons, and by gaining electrons, that makes them an anion. And our elements that are right on the fence of being a metal or a nonmetal are metalloids. And so probably, as you could predict, because they're the fence line between metals and nonmetals, they are going to carry properties of both. And so there's not one set of characteristics for metalloids, but for example, silicon is shiny, which would be a property of a metal, but it is brittle, which would be the property of a nonmetal. So you see a mix of properties between the two. And there's 1, 2, 3, 4, 5, 6, 7. There's 7 metalloids. Be careful not to include aluminum. Although it's right near that staircase, if you think of aluminum foil, we typically view that as a metal. Otherwise, the elements that are touching the staircase, typically above or below, are metalloids, with the exception of aluminum and the exception of acetylene. Moving into other groupings on the periodic table, the vertical columns are called families or groups. And like a family, we can have similar family characteristics, and so do elements in the same family. So we'll learn later that all of the alkali metals are really reactive, and all of the noble gases are not reactive. And so these vertical columns and groups are called families, and we're going to teach you the family names. We mentioned this in Unit 4, but the horizontal rows that we called energy levels in our last unit can also be called periods or rows. I had someone say that like when you write a sentence, you put a period at the end of it. So a way to remember that periods are those horizontal rows might be a way for you to remember that. So in your notes, just let's make a note that horizontal are periods, and these vertical columns are groups or families. A set of blocks that you want to know is the S and P block, are called, another way to call them, instead of S and P, we could call them the representative elements. And the reason they can be called the representative elements is that these are the blocks that represent the valence electrons. And those become super important to us because they can help predict chemical behavior. If something's going to be stable, if something's going to be reactive, who's going to bond with who, is all coming out of the outer electrons or valence electrons. And valence electrons are specifically found in the S and P block. So we can call them the representative elements. Okay, we want you to learn the specific family name for, I think it's about 7 of the families. Not everyone has a specific name. So the ones that we are showing you, we want you to know. So group 1, family 1, is known as the alkali metals. They are extremely reactive. They're typically not found by themselves in nature. Later in this unit, we will show you what happens when we put a little piece of sodium in water. And if we get crazy, we'll even put a little piece of potassium in water. So these are known as the alkali metals. Group 2, right next to the alkali metals, has a very similar name, and they are called the alkaline earth metals. These are slightly less reactive than our alkali metals, also not being found freely in nature. They're just a little harder and denser than the alkaline metals. We jumped way over to the right to group 17. This family is called the halogens. Notice we are to the right of our staircase, so we are in the nonmetal world. And the halogens happen to be the most reactive nonmetals. And you commonly find them in salts, like sodium chloride. Here's our halogen. Here's our alkali metal. Crazy that separately there's both very reactive metals, but in a compound, it's what we put on our french fries. Another family is group 18, and these are called the noble gases. And as we've been learning, noble gases are very stable. They have 8 valence electrons. Therefore, they don't want to react with anyone. So they might be called inert. It just means they're not reactive. Why do they need to react if they already have their 8 outer electrons? So this next one is easier to be referred to as a block, so it's not just one vertical row. And so last unit we knew this as the D block. These are also known as the transition metals. So that middle block is known as the transition metals. They can have multiple charges, which you'll see later, like in Unit 8, and you're going to see properties of metals. The block at the very bottom of your periodic table, we called it the F block in Unit 4. We're going to call them the inner transition metals for Unit 5. The top row is called the lanthanide series, and the bottom one is called the actinide series, and they actually fit inside of that lower part of the D block. But to fit a periodic table on a 8.5 by 11 piece of paper, the periodic table would be too long if it was fully extended, and so the F block got dropped underneath. As we're getting to know groups on the periodic table, one that we mentioned back in Unit 2 that pops up again in Unit 5 are elements that we call diatomics. Di means 2. There are 7 elements on the periodic table. When they are an element, not in a compound, but when they are alone, by themselves, there's always a subscript 2. There's 2 of them. And if you find them on your periodic table, so hydrogen's a diatomic, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Some people call this the magic 7 because hydrogen's a little bit of an outlier, but it pretty much makes a 7. There's other little sayings, but you want to know these 7 elements are called diatomics. Okay, last part of today's lesson. We're actually going to teach you a shortcut to something we taught you in Unit 4. We ended Unit 4 by looking at valence electrons through electron configurations, and then y'all having to determine is it going to gain or lose electrons. The periodic table can actually shortcut this. So if we look, for example, at our alkali metals, all of these would end in S1. This would be 2S1, 3S1, 4S1, 5S1, and so all of group 1 has 1 outer electron. It's also numbered group 1. Group 2 has 2 valence electrons. All of these end in an S2. We're going to skip over our transition metals, and so some renumber this as 3 or 13, and this family everyone has 3 outer electrons. This one has 4. This one has 5, 6, 7, 8. So instead of having to write an electron configuration, you just have to look at the group number, and you now know how many outer electrons there are. Now remember, your periodic table probably says 18, and then I don't remember if it's above or below. It might say 8A. That's the counting if you're skipping that middle block. So it's 1, 2, 3A, 4A, 5A, 6A, 7A, 8A. But that immediately tells you how many valence electrons that family has. So this is just kind of repeat. All of group 1 ended in S1. They all have one valence electron. Now they are not close to having a full outer shell, so they would prefer to lose their one electron, giving them a +1 charge. Group 2, we ends in S2, 2 outer electrons, still want to lose, therefore taking on a +2 ion. Group 13 would have a full S sublevel and then P1. And so if we added our S and P, we'd have 3 valence electrons, still losing +3. Sorry, my handwriting looks like chicken scratch. Here we would have S2P2. I'm just going to keep going. S2P3, S2P4, S2P5, S2P6. So now 2 plus 2 is 4 valence, 5 valence, 6, 7, 8. So 4 is halfway to 8, so this is where you can gain or lose, plus or minus 4. Now this is your halfway point. Family 15, group 15, they have 5 outer electrons. They would not be in their advantage to lose 5, but rather gain 3 more electrons. Electrons are negative, therefore it takes on a -3 charge. Group 6 wants to gain, this time they only need to gain 2 electrons. The halogens, group 17, want to gain that 1 electron. Oh, got ahead of myself. Gain 1 electron. And then group 18, trick question, they do not want to gain or lose. They do not have a charge because they are stable. So something that's going to help you in the future to get good at this is to go ahead and write your charges above your families. So alkali metals are a +1 charge, alkaline earth is +2, skip over that D block and you have +3, plus or minus 4, -3, -2, -1, 0. I don't know why my negative. I've heard it explained it's like you're going up a mountain and then going back down. It's +1, +2, +3. At the top of the mountain, you're either plus or minus 4, and then just mirror, go down the mountain, -3, -2, -1, 0. And then if you just like extend that line back to being flat, you've written out the charges on your periodic table. So valence electrons are really important in chemistry. Like I said before, it helps us see why elements might be reactive or not reactive and how they're going to bond. And so a quick way for us to look at valence electrons, besides looking at your periodic table, is something called a Lewis dot diagram. And it's 3 easy steps. You write the element symbol, you determine the number of valence electrons based off your periodic table group number, and then you fill according to Aufbau and Hund's rule. So throw back to Aufbau. He's the one that said you have to fill the lowest energy level, lowest sublevel before moving on. So what that translates to Lewis dot diagrams is that your first 2 valence electrons has to go on top first. Okay? And then Hund's rule was if you were in equal energy level, sublevel, electrons would want to space out before having to double up. So if you had 5 valence electrons, it would look like this layout. The first 2 on top, 1, 2, and then 3, 4, 5. If you had 6 valence electrons, you'd add a 6, add a 7, add a 8. This is the max your Lewis dot should ever look like. Sometimes y'all get crazy and I start seeing 16 dots. The max number is 8 valence electrons. So let's use our periodic table and see if we can figure out the valence electrons for the following elements and draw their Lewis dot diagram. Okay, Na, sodiums. Find sodium on your periodic table. It is far left on the alkali metals, group 1, so it has 1 valence electron. Get a bigger dot. Okay, magnesium. Really close, alkaline earth, group 2. Oh, I went real big. Okay, magnesium has 2 valence electrons. Aluminum, group 13, has 3 valence electrons. First 2 go on top, and then 1 goes on the side. Carbon is group 14, 4 valences. First 2, 1, 2, 3, 4. If you did not space that out, you would lose credit on your Lewis dot diagram. You need to be following Aufbau and Hund's rule. Let's go nitrogen. It's in group 15, which means it has 5 valence electrons. So 1, 2, space it out, 3, 4, 5. Oxygen is in group 16, which has 6 valence electrons. 1, 2, space it out, 3, 4, 5, double up 6. Fluorine is a halogen, group 17, therefore has 7 outer electrons. It's so close to being stable. It has 1, 2, 3, 4, 5, double up 6, double up 7. And then neon is our full group 18, 8 electrons, so 1, 2, 3, 4, 5, double up 6, double up 7, double up 8. What does a Lewis dot diagram look like for ions? So a potassium ion, so potassium is an alkali metal, group 1, has 1. So it wants to give away that 1 electron. And so for now, we're just going to keep this totally empty. It gave away its 1 outer electron. And we call that a cation because of that positive charge. Neutral bromine is a halogen. It has 7 valence electrons. It's so close to being stable. So it's ultimately going to want to gain 1 electron. And so your Lewis dot diagram would reflect that. So I'm going to get fancy, change up the gained color. And so by taking on an extra electron, it's a little more negative. The N in anion can stand for negative charged ion.